Okay, welcome to the deep dive. We're pulling up a really interesting source document today.
Yeah, what we got?
It's an orientation guide specifically made for chemical engineering students, right before they head out for their industrial internships.
Ah, right. So not just a syllabus then, more like a practical roadmap.
Exactly. It's designed to bridge that crucial gap between what you've learned in lectures, labs,
and the sometimes chaotic reality of a factory floor. Or, the controlled reality anyway.
Precisely. So our mission, really, with this deep dive is to unpack this document. We want to get to the heart of why these internships are just so vital for chemical engineers like you listening.
And, crucially, how all that theory, all those equations and concepts you've crammed, how they actually come alive. And they sometimes maybe look a little different when you see them applied on a massive industrial scale.
Think of it like getting a shortcut. Instead of feeling totally lost, stepping from campus onto some huge plant floor.
Yeah, that can be intimidating.
This document is meant to be your guide, helping you see how those abstract concepts you studied are actually controlling huge processes right there in front of you.
Okay, yeah, I like that framing. A guide.
Okay, let's unpack this then. The document, it jumps right in, doesn't waste time on the core purpose.
Right.
It frames internships as way more than just, ticking an academic box. They're called the first real step into the industry. Why is that framing so important, do you think?
Because it sets the stage, really. You spend years mastering equations, principles, running maybe tiny lab experiments.
Right, bench scale stuff.
But that first step into a real plant, that's where you finally see those exact principles working. But at a scale you've probably never even imagined.
And the source uses some great really concrete examples right away to make that point. It talks about being in a brewery, right? And seeing how chemical thermodynamics isn't just cycles on paper.
No, it's the absolute critical control for your fermentation temperatures. Get that wrong, and the product's ruined.
Or walking through a soft drink factory and seeing fluid mechanics, not just equations, but actually governing how materials move super fast through maybe kilometers of pipeline.
Yeah, and without that practical exposure, during the internship, making that mental leap from a beaker to a, 50,000-liter reactor.
Huge difference.
It's really difficult. The internship makes the abstract suddenly very tangible.
So beyond just bridging that theory-practice gap, what other big benefits does this document highlight for you, the intern?
Well, building industry-specific skills, that's a huge one.
Okay.
The document points out pretty clearly that textbooks just cannot teach you the nuances, like how to actually operate and troubleshoot equipment that's specific to one sector.
Right, like mastering the exact evaporation techniques they use in a sugar factory. That's not in every textbook.
Exactly. Or figuring out the complex operation of a massive distillation column in an oil refinery. These are hands-on skills.
Things like actually reading a P&ID.
Oh, essential.
Yeah.
That's your piping and instrumentation diagram, your map of the whole process, how it's controlled.
And troubleshooting a pump that's suddenly failing. Or maybe optimizing a reaction based on live feedback.
Real-time adjustments, Stuff you learn by doing.
And the document, it really emphasizes getting a deep understanding of safety and operations.
Calls it crucial, which in chemical engineering it absolutely is, non-negotiable.
It points to the serious safety focus in many Ethiopian industries. Specifically mentions breweries, soap factories as examples.
Places where you'll learn about things like HAZOP studies.
Hazard and operability studies, that structured way to find risks before they happen.
And seeing why mandatory PPE, personal protective equipment, isn't just a suggestion.
No.
And understanding emergency management protocols. And the document makes a really sobering point here.
Yeah.
This knowledge isn't academic. It could potentially save lives, yours or someone else's.
Wow. Okay. And then there's the career angle. The document's pretty direct about that, too.
Very direct. It says many Ethiopian companies, they actively recruit from their intern pool.
And it names names like East African Bottling, that's Coca-Cola, Mugger Cement, Mayu Arosi Oil.
Yeah, suggesting that if you perform well, you could genuinely get a job offer even before you graduate.
Which is huge. Plus, the engineers, the operators you meet, they become contacts, potential mentors.
References for the future. Invaluable network.
Definitely. And finally, it's a critical chance for, career path discovery.
Right. You might think you know what you want to do.
But the internship lets you actually test that idea. Maybe try process control in a dairy plant. or explore environmental engineering at a wastewater facility.
See if it really fits you before you commit to a full-time job. It's a low-risk way to make a potentially high-impact career decision.
So wrapping up this first bit then, the internship experience, it fundamentally reinforces how interconnected all your core chem-eng courses are.
Thermodynamics, fluid mechanics, reaction engineering, all of them.
It forces you to see them working together in real systems.
Which enhances not just your technical skills, but your problem solving, your critical thinking.
And professional communication too, presumably.
Absolutely. You have to explain complex things clearly.
Okay, that leads us perfectly into the real core of this deep dive then.
Yeah.
How do those connections actually look in practice? The orientation doc gives this fascinating course-by-course breakdown.
Yeah, it's like a checklist, almost a treasure hunt for finding applied knowledge in the wild.
So where do we start? Chemical engineering, thermodynamics.
Yeah.
You study the laws, the cycles.
Mm-hmm.
How does the plant bring that stuff to life?
Okay, so the document says, seek out the equipment, the actual hardware. Heat exchangers, condensers, evaporators. They're not just symbols anymore.
Right. You'll see maybe shell and tube heat exchangers actually cooling beverages at East African bottling.
Or at Mr. Mosi Oil, you might spot plate heat exchangers recovering waste heat. And suddenly, concepts like the overall heat transfer coefficient in your equations, and how things like, say, corrugated plates drastically improve heat flow compared to just smooth pipes, it becomes real. You see the design choice.
And in a sugar factory, those huge evaporators concentrating syrup, they visually demonstrate boiling point elevation.
And the massive amount of latent heat, that H of G, enthalpy of vaporization involved in just changing phase from liquid to vapor.
What about refrigeration? We study the cycles.
Yeah, the vapor compression cycle. But seeing it precisely control fermentation temps at, say, Heineken or BGI Ethiopia breweries, that shows its critical role in product quality.
And for really critical stuff, like ensuring drug stability at Addis pharmaceutical factory, maintaining that tight temperature control is absolutely non-negotiable.
Exactly. And the document pushes you further. It asks you to analyze things like, how does the actual coefficient of performance, the COP, of a real system compare to the ideal Carnot cycle?
So you're forced to deal with real-world inefficiencies, friction, heat leaks.
Exactly. Why isn't it perfect? And a key thing the document stresses is analyzing real process data. Don't just look at the shiny equipment.
Look at the numbers, the temperatures, pressures displayed.
Yes. Check the inlet and outlet temps on a heat exchanger. Do a quick heat duty calculation in your head or notebook. Does it match what the process needs?
Or visually spotting missing insulation on a steam line that's literally seeing lost work from the second law as wasted energy.
Right. And comparing instrument readings, pressure, temperature, flow rates to your classroom calculations becomes this practical check. Validation. Troubleshooting even.
And seeing the plant instrumentation, the gauges, the screens.
It's not just about buttons. Those gauges ensure reactor conditions stay within safe thermodynamic limits. The DCS screens your distributed control system.
The brain of the plant.
Right. Monitoring a distillation column, they might show temperature profiles that literally illustrate vapor-liquid equilibrium happening across different trays.
Observing phase changes at scale must be pretty impactful too.
Definitely. The document points to distillation column trays in an oil refinery as like physical versions of those theoretical stages you calculated with McCabe-Thiele diagrams.
Showing how equilibrium is approximated in a real dynamic system.
Yeah. Or watching steam condense in a huge power plant condenser and just appreciating the immense enthalpy change, that HFG being released.
Energy efficiency seems like a constant theme.
Always. Identifying where useful energy is lost, steam leaks are basically exergy destruction in action.
Right.
Heat losses show why insulation calculations matter, and seeing if the plant operations actually align with the first and second laws in practice.
And understanding why equipment was designed a certain way must solidify the theory.
Totally. Baffles and heat exchangers. They aren't random. They're there to induce turbulence, which massively boosts that heat transfer coefficient.
Coiled condenser pipes maximize surface area. Vacuum evaporators lower boiling points.
Which is a direct application of vapor pressure versus temperature curves, saves energy by letting you evaporate at lower temps.
And the document says interns should actively look for energy recovery opportunities.
Yeah. Seeing exhaust gases preheating boiler, feed water at Mugger Cement. That's real-world pinch analysis. Reusing condensate steam for heating elsewhere. Simple, effective heat integration.
So the core message for thermodynamics, according to this guide, is making the abstract concrete. constantly asking.
How does this kit, this reading, this step relate back to the thermo I studied? It forces the connection.
Okay, shifting gears slightly. Fluid mechanics and fluid machines. This is all about moving stuff around, right? Liquids, gases.
Exactly, moving and controlling fluids at scale.
So you'll spend time identifying, understanding the basic components. Pumps, compressors, valves, flow meters.
Seeing them actually running, observing fluid flow in massive pipes, in process units, it's different from a diagram.
And critically, monitoring the actual measurements, pressure, flow rate, velocity.
Which lets you analyze things like friction losses, pressure drops that always happen in real pipes. They're never perfectly smooth or straight like in the textbook problems.
So applying concepts like Bernoulli's and continuity equations, it's not just for problems anymore. You see the principles at play.
And interpreting those P&IDs, the piping and instrumentation diagrams, understanding the symbols, the lines, becomes like a survival skill for navigating the plant.
Which all directly supports troubleshooting, maintenance for fluid handling gear.
It makes you really aware of the safety aspects, too, when you're handling huge volumes of potentially hazardous fluids.
And it opens doors to maybe contributing ideas for efficiency or system optimization.
Definitely. Little tweaks can save a lot of energy in pumping systems.
Okay, moving into solids. Handling them, separating them, mechanical unit operations.
Right. Here you'll be looking at bulk solid handling systems. Things like conveyors moving materials, hoppers storing them, feeders controlling the flow rate.
You'll see size reduction equipment crushers, mills actually working, maybe size enlargement too, like extruders or granulators.
And analyzing how particles flow, how segregation can happen in a hopper or chute, that becomes a practical observation, not just a theory.
You'll study screening, classification methods, seeing equipment like cyclones or sieves separating particles by size in real time.
Fixed bed operations common in reactors or adsorption columns show you real-world pressure drop, flow distribution challenges.
Maybe fluidized beds, if you're lucky.
Yeah, understanding that transition to fluidization, seeing how well they mix things, transfer heat or mass, and observing filtration, sedimentation equipment filters, clarifiers, centrifuges, and solid liquid mixing.
Building on that, thermal and mass transfer unit operations, separations, exchange processes.
You'll revisit heat exchangers, evaporators, condensers, yeah. But now the focus shifts slightly. You're evaluating their actual performance in the plant.
So monitoring temperature gradients, assessing the real heat transfer efficiency, different from calculating ideal numbers.
Very different. And mass transfer operations, distillation columns, absorption towers, liquid extractors become live processes you're analyzing.
You see how those heat and mass transfer coefficients, which were just abstract numbers in class,
directly influence how well these units actually perform in practice.
Interpreting process flow diagrams, PFDs, that involve these transfer units is essential then.
Absolutely, to understand the whole picture. And you learn to spot real-world problems like fouling or scaling on heat exchange surfaces.
Stuff that kills efficiency.
Exactly. Or inefficiencies in separation columns. This practical view lets you help with troubleshooting, do basic checks, maybe even suggest improvements or energy savings related to these transfer ops.
Now, at the heart of many chemical plants, reaction engineering.
Yeah, this is where the chemistry happens on a big scale.
You'll get to observe industrial reactors batch, CSTRs, continuous stirred tank reactors, PFRs, plug flow reactors.
And understand their specific operations in a live process. Crucially, you see the real-world reaction conditions being maintained, temperature, pressure, how catalysts are used or handled.
Monitoring conversion, selectivity, yield in a continuous process. That sounds way more complex than a lab bench experiment.
Oh, it is. You see how reaction kinetics, identifying the rate-controlling steps, how that directly informs how operators run the process day to day?
Applying material and energy balances over these big, complex reactors must be a practical necessity.
For monitoring, for optimization, absolutely. You also learn how catalyst performance is watched, how to spot signs of deactivation when it starts losing its punch.
This experience helps you understand scale-up considerations then.
Yeah.
From pilot plant to full size.
Definitely. And how to troubleshoot common reactor problems, the specific safety measures needed for reacting systems. You might even get involved in optimization discussions or look at pilot-scale data.
Okay, stepping back a bit now to see the whole picture. Process industry is viewing the entire integrated system.
Right, seeing how it all fits together.
This is where you're mapping the overall process flow diagram, the PFD, for the entire plant. Tracing material flows, doing overall material balances.
And you start seeing practical realities, like maybe unexpected waste streams, molasses coming out of a sugar factory or away from a dairy plant and figuring out where they go.
You get a comprehensive understanding of the whole production process, from raw materials arriving
to final products being shipped out. You identify where those raw materials come from. Are they local, imported? You might even map their sources.
You see how all those individual unit operations we just talked about are actually integrated into one functioning system.
And you learn industry-specific technologies, best practices that aren't generic. Every industry has its quirks.
Analyzing overall process efficiency, spotting bottlenecks that limit production, understanding material handling logistics across the whole site, that becomes clear.
You grasp the importance of quality control, quality assurance throughout the entire chain, and you see environmental and safety regulations being implemented.
You might even support documentation, like updating SOPs, standard operating procedures, or contribute ideas for overall improvement or waste minimization.
It's about that big picture view.
Which connects nicely to basic environmental engineering. Hugely relevant, especially in growing economies.
Absolutely critical.
You'll observe wastewater treatment processes, the equipment they use. The document gives examples like seeing how textile factories treat dye wastewater.
Using sedimentation, biological methods, maybe coagulants.
Or how breweries test their wastewater checking pH, BOD, CO'd, making sure they meet standards, like EPA standards, and what actions they take if they don't.
Understanding how air, water, solid waste are managed becomes concrete. Seeing bag filters controlling dust at a cement plant, or how they handle the kiln dust.
Identifying pollution sources and their controls becomes visual. Maybe tracing chromium wastes in a tannery and seeing the recovery system designed for that specific hazard.
You learn the specific regulations for that industry. Effluent discharge limits for a sugar factory, for example.
You might support emission monitoring, like witnessing stack testing at a steel mill.
Or participate in waste minimization efforts, seeing coffee husks from a processing plant repurposed as fuel or fertilizer. Direct application of sustainable principles.
Assessing safety and environmental risks in practice is vital too, like understanding ammonia storage risks at a fertilizer plant, seeing the containment measures.
And you can contribute to sustainability initiatives, like suggesting water conservation in a beverage factory. It's all about protecting those natural resources.
Yeah, okay, process dynamics and control. This is where we see automation and stability in action.
Yeah, keeping things running smoothly and safely.
You'll observe the control systems, PID controllers, those proportional integral derivative ones.
The workhorses, yeah. And the sensors measuring things, the actuators making changes, all operating in real time. Think of a PID loop automatically adjusting fuel flow to keep a cement kiln at the perfect temperature.
Understanding how key variables, temp, pressure, flow, level are monitored and controlled becomes clear.
You see why precise temperature control is vital for brewery fermentation quality, how pressure sensors keep bottling lines running, how flow meters track water use for efficiency.
You'll monitor system responses, like how things stabilize after a change.
Yeah, observe how a textile dyeing unit gets back on track after maybe a power flicker or a change in dye concentration. Interpreting control loops on PIDs becomes second nature.
Tracing how, say, a tank-level signal controls an upstream valve in a sugar factory's evaporation system.
Identifying and managing process disturbances, that's a constant challenge. Like how a pharma plant handles variations in raw materials affecting tablet compression. Might be automated compensation, might need operator tweaks.
And you learn about the automation systems themselves. PLCs, DCS, SCADA.
Programmable logic controllers, distributed control systems, supervisory control, and data acquisition. Seeing SCADA monitor refrigeration across a whole flour processing plant, or PLCs automating gas injection for ripening.
And this experience lets you contribute, maybe suggesting adjustments to PID tuning.
In an oil refinery, perhaps, or understanding how safety interlocks automatically trigger shutdowns, that links right back to safety management.
The chemical engineering apparatus design, then, moving from drawings to the actual physical equipment.
Understanding the why behind the design choices for reactors, heat exchangers in that specific plant.
The doc uses the example of a sugar factory evaporator design.
Right. Why was that design chosen? Considering heat transfer needs, pressure drop, but also corrosion resistance for sugary liquids.
Reviewing real equipment specs, engineering drawings, industry standards, suddenly those appendices in textbooks matter.
Checking pump specs, pipe routing drawings in a textile plant becomes practical work.
Observing material selection. Why refractory bricks in a cement kiln?
Because they need to handle extreme temperature, abrasion, and be cost-effective. You see the trade-offs. And you identify real-world design limits, like a brewery fermentation tank volume being constrained by the building size.
You might even assist in basic design calculations for existing gear.
Maybe calculating the required thickness for an ammonia tank in a fertilizer plant based on its pressure. Learning about fabrication, installation, testing, seeing stainless steel reactors made, or pressure testing done in a pharma factory.
Participating in troubleshooting that leads to equipment modification sounds like great experience.
Diagnosing why a heat exchanger in an oil plant keeps fouling, then suggesting changes to the cleaning cycle or even the material, and supporting documentation, like updating manuals for a tannery's wastewater system. Important stuff.
Computer-aided process design and simulation, taking software skills into the plant.
You might actually get to use simulation software Aspen Plus, HYS, AFES-WISE, ChemCAD to model what's happening right there.
Simulating specific units, distillation columns, heat exchangers, reactors using real plant data.
Exactly. Performing material and energy balances with the software, feeding it numbers collected from the plant, might involve helping develop or review PFDs and PNIDs made with design software.
And a key use is analysis and optimization.
Using simulation to explore what-if scenarios, find more efficient operating points without messing with the actual plant, and crucially, validating your simulation results against actual plant performance data, seeing where the model works and where it needs tweaking.
Okay, plant design and economics, where engineering meets the bottom line.
You observe how real plants are designed and run, which is often a compromise. Theory versus cost, space, practicality.
Understanding the market landscape, company position, competitors, demand, how that influences production targets.
Yeah, and capacity planning becomes real. Seeing how production capacity is set, identifying bottlenecks like getting raw materials to a cement factory on time.
Reviewing actual PNIDs, comparing the plant layout to design principles for safety, efficiency. That gives valuable perspective.
Flow sheeting means tracing those PFDs in the plant, identifying recycle streams, bypass lines, utility connections, steam, water, power.
Collecting real plant data to check mass and energy balances, seeing energy recovery systems working, learning about CapEx and OpEx capital and operating expenditures, how costs are estimated, how savings are found.
If you're involved in project talks, you might see economic evaluations. Payback period, ROI, net present value, NPV, used to justify spending money.
Learning about depreciation methods, how they hit the financial reports, gives business context.
Studying how the time value of money applies to plant investments. Observing how expenses are tracked, fixed costs like rent versus variable costs like raw materials.
And understanding site selection. Why is the plant here? Logistics, raw materials, labor. Analyzing the layout for safety, ergonomics, maybe seeing how rearranging a pharma packaging line improved things.
Process integration and optimization. Finding smarter ways to connect things up.
Actively identifying energy and material integration opportunities, like using hot wastewater from one process to preheat cane juice in a sugar factory. Classic integration saves loads of steam and fuel.
Analyzing process flows to cut waste, boost efficiency. Like countercurrent washing in a textile dyeing plant uses way less water and chemicals than single pass.
Applying pinch analysis concepts, seeing waste heat from a cement kiln exhaust used to dry raw materials.
Improves thermal efficiency, cuts down on burning extra fuel like coal. Evaluating resource recovery, waste minimization can be a source of savings or even revenue.
Like repurposing brewery spent grain for animal feed or biogas, turns waste into value.
Assisting in simple stuff, like finding and fixing steam leaks in a soap factory. Directly cuts energy waste and bills.
And contributing modification ideas. Suggesting a heat exchanger in a steel mill to capture heat from cooling billets to preheat incoming ones.
Reduces furnace fuel use. It's all about thinking systemically.
Sustainable resources and energy. Focus on responsible, efficient operations.
Identifying energy conservation, efficiency opportunities everywhere. Seeing a waste heat recovery system at a cement plant making electricity or preheating stuff cuts fuel costs, emissions, maybe supporting evaluation of renewables, feasibility of solar thermal or biomass for steam in a textile factory, reduces reliance on fossil fuels.
Analyzing resource usage, water, energy, raw materials, how it's tracked. Seeing a brewery track water use, implement recycling or low-flow nozzles, cuts usage and costs.
Assisting with waste reduction, resource recovery. Exploring chromium recovery in a leather plant, or eco-friendly tanning agents. Addresses a major waste issue, saves money. Evaluating the carbon footprint, environmental impact. Analyzing ammonia emissions at a fertilizer plant might lead to talks about carbon capture or offsets like tree planting.
Participating in energy audits.
Yeah.
Like identifying old motors in a sugar factory for replacement with high efficiency ones can slash power bills.
Proposing sustainable improvements. Researching how fruit peels from a food processing plant could be composted for biogas or animal feed. New revenue, less landfill. And learning about the company's broader ESG practices, environmental, social governance.
Like a pharma company reducing solvent emissions, supporting local health, ensuring fair wages.
Production and project management. The operational backbone, how the plant runs day to day, how improvements get done.
Understanding production planning, workflow coordination, seeing how raw material deliveries sync with operations at a cement factory to avoid holdups.
Observing scheduling, inventory management, resource allocation in practice, assisting in monitoring productivity, quality metrics, identifying causes of downtime.
Like recording loom stoppages in a textile factory, analyzing why. Directly helps efficiency. Learning project planning tools like Gantt charts may be used for planning that dying unit expansion.
Participating in team meetings discussing delays, adjusting schedules at a food plant shows the collaborative side. Supporting cost estimation, budget tracking, comparing actual energy costs to budget links engineering to finance.
Identifying process improvements for efficiency. Rearranging packaging lines in a pharma factory to cut waste, downtime. Understanding KPIs, key performance indicators for safety, quality production. Reviewing batch records against FDA standards in pharma.
And finally, industrial safety and loss management, arguably the most critical subject.
Absolutely. Hazard identification and risk assessment aren't just theory anymore. You'll learn the specific chemical, mechanical, thermal hazards there. Investigate near misses, past accidents, understand formal processes like HAZOP studies.
Process safety management, PSM, comes alive. Seeing if critical safety layers, interlocks, alarms, PRVs, vent systems are properly maintained, working. Observing how flammable or explosive materials are stored safely.
Fire and explosion prevention measures become visible. How flammables are contained, explosion-proof electricals in hazardous areas, understanding dust explosion risks. Chemical storage and handling means seeing proper segregation, secondary containment like bund walls, ensuring NSDS sheets are accessible.
Machine safety means seeing guards, understanding and using lockout, tagout, LOTO during maintenance. Ensuring gear is safely de-energized. Monitoring noise levels. Emergency preparedness means knowing exits, extinguishers, eyewash stations, doing drills.
PPE compliance is non-negotiable. Everyone wearing the right gear, knowing how to maintain it. Considering ergonomic risks, too. Environmental and occupational health means monitoring airborne contaminants, controlling noise, vibration, ensuring ventilation, especially in confined spaces.
Loss prevention and waste minimization ties safety to efficiency. Spotting material losses like spills, energy waste through leaks, exploring byproduct recycling.
And critically, looking at behavioral safety. Potential training gaps. Are protocols ignored? Is training outdated? Is there a real safety culture where everyone looks out for each other?
And the last point the document makes is applying research method and experimental design within the plant context.
Right, not just academic skills, but tools for investigating, improving real problems.
The document lists common areas in industries like those in Ethiopia. Import substitution comparing imported versus local raw materials for cost, quality.
Waste valorization, identifying waste streams, exploring recycling or repurposing options, checking regulations, turning cost into revenue.
Energy loss recovery and efficiency, doing mini audits, finding leaks, inefficient heaters, oversized care, proposing waste heat reuse.
Process optimization and yield improvement, finding bottlenecks while yield is low, analyzing byproducts, reducing rework.
Water conservation and recycling tracking usage versus discharge, evaluating reuse options, finding leaks.
Pollution control and emission reduction. Investigating stack emissions, untreated wastewater, addressing odor or particulate complaints.
Safety and hazard mitigation, applying structured methods to understand accidents, near misses. Identifying bad storage practices, outdated protocols.
And product quality and consistency, analyzing customer complaints, why products fail standards, investigating batch variations.
These are all areas where that structured thinking from research methods can solve real, impactful industrial problems.
Wow. Okay, stepping through that document course by course, it really underscores how comprehensive this internship experience is meant to be.
Yeah.
Just makes it crystal clear that this practical time fundamentally connects all those concepts you learned.
It absolutely does. And, it makes your future coursework so much easier to grasp because you suddenly have real reference points in your head.
You've seen it.
Exactly. And it builds those essential professional skills, observing, analyzing, communicating that textbooks just can't teach you in the same way.
And the main strategy this document pushes is just Aggressive, active observation. And constant questioning while you're there.
Yeah, don't just clock in and out.
Yeah.
Actively look for how the theory is applied. Ask why. Ask how does this work? Ask what if.
It truly transforms the internship from just, fulfilling a requirement.
Into this deep, active learning experience that genuinely shapes your engineering intuition in ways nothing else really can.
So thinking about that sheer breadth of application you encounter.
Yeah.
Just in one plant.
Yeah.
From fine-tuning a PID controller on a fermenter, to mapping waste streams for valorization, or just understanding why that heat exchanger was chosen.
Yeah.
How might focusing deeply on just one of those practical areas, asking all those why questions, fundamentally change your understanding of a complex engineering principle you thought you already knew cold from the textbook?
Oh, it often reveals layers you never even considered. Complexity, real-world constraints.
Like cost, safety, space.
Exactly. The theory gives you the foundation, the framework, but the plant adds the crucial dimensions of scale, safety, economics, and just messy reality. It's never quite as neat as the book.
Absolutely. And that's why engaging with source material like this guide, which tries to bridge those two worlds, is such a powerful way to learn.
Couldn't agree more.
Thanks for joining us for this deep dive.